Thank you, Jiayi Zhao. I apologize for not being able to attend in person due to visa issues. Good morning, ladies and gentlemen. Today, I will present on the topic Reconstructing Ear Canal Channels for Fine-Grained Detection of Tympanic Membrane Changes. I am Yongzhi Huang, from the Hong Kong University of Science and Technology. First of all, let me introduce our background, the ear's structure, and its self-protection mechanisms. We focus on the outer and middle ear, especially the ear canal and tympanic membrane. The canal is not a straight tube. It is S-shaped, with changing cross-sections and bends, and it ends at the eardrum. These geometric and boundary variations create distinct acoustic reflections for each person. Even small changes like swelling, wax position, or posture can shift the reflection pattern. This complexity is exactly why we build an individual digital twin of the canal instead of relying on a single global model. Inside the cochlea, we can see that it is a remarkably complex structure. Tiny hair cells convert vibrations into neural signals. In humans, once these cells are severely damaged, they are unable to regenerate. Noise exposure, infections, or ototoxic drugs can cause cumulative loss. Since the damage is mostly irreversible, prevention and early warning are essential. So, we monitor changes in the canal tympanic transmission so we can flag risk or abnormal states before lasting inner ear damage accumulates. The middle ear has a built-in safety valve, which is the acoustic reflex. When sound is loud suddenly, certain structures in the ear, specifically, some parts of the muscles contract, stiffening the tympanic membrane. The changes raise the effective impedance and reduce the energy transmitted to the cochlea, acting as a form of self-protection. So, we want to read those tiny changes, update the ear's digital twin. Because the reliable clues live in the acoustic reflections shaped by canal geometry and boundary impedances. So we reconstruct a per-ear canal channel state information, which serves as our ear's digital twin. Then we can compare its prediction with the actual measurement. To calculate the CSI of the ear canal, there should be 4 steps. First, we reconstruct the ear canal. We estimate the length and shape, and we obtain a clean channel model. Second, we send a gentle wideband probe inside normal audio. It reveals the reflection fingerprint. Third, we keep it stable in daily life. We handle device response, fit, and noise. Fourth, we compare prediction and measurement. The first instinct is timing. However, we found that timing on phones is fundamentally unstable, because playback and recording do not start together. Just like we try to time a firefly's blink with a kitchen clock, that is the time of flight on phones. The ear canal echo lives in microseconds. Consumer audio adds unsynced playback and record, codec buffers, and OS jitter. So, even if our code uses some sync methods, the system does not. See Figure 8. The result is a meter scale error. That is a large difference from our centimeter scale canal. Another challenge is the canal itself. Sound does not follow a single, direct path. It reflects. It diffracts. It scatters. The return is a mix of many paths. Peaks and valleys in the spectrum shift. So a single echo time or a single delta F is not reliable. Both the device and the canal inject noise, so raw spectra are unstable. So we switch to a new solution, a convergence strategy. We first bracket the canal length. The upper side is easy. Multipath reveals the longest route. The hard part is the lower side. We turn the mic's finite aperture into an angle cue. In the near field, it acts like a spatial filter. When the incidence angle changes, the fringe spacing in the spectrum shifts. We read that shift, recover the angle, and get the canal axis projection. With that projection, we draw the shortest path and obtain a stable, lower bound that does not move with volume or playlist. Now we have an upper bound and a lower bound. We bracket first, and then iteratively tighten, converging to the true canal length. These are the specific calculation methods. We can see very good results in different types of ear canal experiments. The second challenge is that canals of the same length but still sound different because their shape are different. The ear is a tapered, irregular duct. If we pretend it's a straight straw, the spectral fingerprint looks too clean and we miss subtle cues. To catch micro changes, we need the area profile, not just a single number for length. We model the ear canal with fluid mechanics intuition and design a detection method. Why does it work? Let us picture a river. A narrow reach speeds up. A wide bay calms down. Cross-section changes in the canal act the same. They alter acoustic impedance and create tiny reflections that leave readable stripes in the spectrum and group delay. We then slice the canal into short segments. For each slice, we estimate the small reflection and march inward from the entrance to the eardrum. This gives a cross-sectional area profile rather than just a single length. To keep it reliable, we score every mark by SNR and phase consistency. We add a global smoothness constraint so the profile is stable and physically plausible. This is the second innovation. We turn fluid mechanics intuition into a practical, per-ear area map. We do it in 4 steps. First, ping with a short wideband probe to get the canal response. Then turn stable spectral stripes into a reflection ladder. Next, slice and march inward to recover the area profile with global smoothing. Finally, forward to ear canal CSI, and report the residual and confidence. While the recursive reconstruction based on reflection coefficients is theoretically feasible, it becomes computationally intensive at high-resolution frequency responses. How to improve the computational efficiency of the algorithm while ensuring accuracy? We propose a novel method for inferring geometry from rapid reflection patterns. We linearize the recursive term with a Taylor expansion. This turns long chains of division into multiplication and addition operations. Multiply and add run faster and stay more stable on commodity audio hardware. We plug the linearized form into the area update and get a division-free approximation. It parallelizes well and avoids numerical jitter. Taylor can grow long. We keep it short with a data-driven cutoff. When a term is tiny, we drop it automatically. The result keeps accuracy while cutting computing time. While the introduction of Taylor expansion improves the stability of local computations, we still face a bigger question. Can the robustness and accuracy of reconstruction be further improved from a global perspective? The reason why we have this question is that, even with better local recursion, it remains a local greedy algorithm, computing segments one by one, which imposes limitations. If a slight local deviation occurs, it can accumulate into poor global accuracy. Local Taylor updates give a quick sketch. Under noise and multipath, several similar profiles can fit the same stripes. We eliminate ambiguity by adopting a single, unified objective that combines data and physics. The profile must fit measured reflections across bands, stay within a plausible length range, and remain smooth like a real tube. From the sketch, we run a constrained, regularized gradient to one stable area map. From the results, we can see that the reconstructed CSI can be aligned, and the shape of the ear canal can be well restored. From the figure, we can see that ear CSI is based on the estimated cross-sectional area reconstructed from the reflected signal in the frequency domain, and the reconstructed curve closely approximates the actual curve. In this paper, we also solve some robust challenges. Even if the algorithm model achieves high accuracy, various unfavorable factors will inevitably arise in real-world applications, potentially affecting detection reliability. When wearing headphones in everyday environments, the sound signal is often not as clean as in a laboratory and is subject to various interference factors. Key interference factors include background noise, motion interference, unstable headphone positioning, and nonlinear distortion. We need to design targeted strategies to mitigate interference and ensure ear CSI remains reliable in real-world scenarios. First is the signal dispersion caused by the hardware system, such as transducer group delay and codec buffering. We designed a multi-level interference compensation strategy and built an interference suppression module to take targeted measures against different interference sources. Due to signal dispersion, we set time windows and link dispersion constraints. The background noise and headphone leakage compensation are another problem we met. So we use frequency domain adaptive denoising to extract stable ear canal response components from the mixed signal. When we put on the earphones, people may shift, leading to unstable wear. Unstable earphone wear and movement introduce artifacts that require correction to avoid false alarms. We design a method to find it. Our process is straightforward. We use the phase change rate of the frequency response as the core cue. The reason is that the earbud shift causes an overall phase shift or slope change. We found that not only does the angle change, but the earbuds can also loosen or shift, leading to signal issues and leakage at low frequencies. The reason is that the motion-induced seal changes modulate the ear canal acoustics as a slow, time-varying gain. This primarily affects low-frequency pressure buildup due to the acoustic high-pass leak effect. During the signal recording, we encountered some fault alarms. Sometimes, and I have to say very rarely, there is some nonlinear distortion in the signal. In real use, the mic, preamp clips, and parts of the waveform turn nonlinear. Classic polynomial fitting looks neat, but it often rings and creates runga oscillations. We take a lighter path. First, we perform bandpass decomposition, then apply cubic spline reconstruction to each subband. We then perform amplitude calibration based on the gain ratio between the original signal and the microphone signal. This approach is lightweight and interpretable. Here is another problem. The same ear shifts under different temperatures and humidity, so a raw day-to-day comparison can fail. We design a new way, FID alignment. Each user has a personal reference distribution, like a white balance. FID aligns the observed feature distribution under changing environmental conditions to a fixed reference distribution by learning a transport map that removes nuisance factors such as nonlinear sensor distortion and temperature and humidity drift. After alignment, the discriminative structure, such as peak spacing or spectral envelopes, is preserved while environment-induced shifts are cancelled. This is the setup for our system deployment. Here is our validation path, from simple to real. First, the COMSOL simulation. Then, a controlled sound pressure tube was used as a clean baseline. Next, silicone ear canals to model geometry. Then, a head model with headphones is used to check the fit and leaks. Finally, human tests to verify generalization. We also used the scanned ear canal for our experiments. We built a diverse dataset. 44 volunteers, 24 male and 20 female, across a wide age range. We compared a high-spec MEMS mic with phone mics to check device effects. All recordings test channel reconstruction, interference mitigation, and health detection. The pipeline operates in real time, and 1-second audio processing occurs in approximately 168 milliseconds. I have to say, this is a meaningful experiment. We test whether ear CSI can detect the acoustic reflex at safe listening levels. The common belief is that the reflex fires only at high levels, typically above 85 decibels. Because our system is more sensitive, we hypothesize that even at everyday levels around 70 decibels, some sensitive listeners may still show a weak reflex. If we can capture this, ear CSI enables a new use case in the future, like personal tolerance profiling, helping each person learn their own ear's actual threshold, instead of relying only on generic standards to set the safe listening levels. We conducted an ablation study to measure the impact of each module. We turned modules off one at a time and tracked classification accuracy and reconstruction error. The result is clear. Remove any one piece and accuracy drops while error rises. Precision, speed, and robustness come from the whole set working together. We analyze in detail the delay of each part of ear CSI and the overall real-time performance on the mobile side. The experiment shows that the average processing time for each module is 168 milliseconds, with the worst case being 500 milliseconds. This indicates that processing is nearly real-time. We tested how ear CSI depends on the input audio. Participants listened to sounds with different spectral shapes. Music, speech, and tonal notes. Wide and narrow bands. The detection stayed consistent across sources and bands. Ear CSI is source agnostic and band robust. It works while you listen. We evaluated ear CSI across different hearing conditions. Across all ear canals, the median accuracy stayed above 77.5%. Specificity was consistently greater than 0.8, indicating a low rate of false positives. These results show ear CSI remains effective across severities, not just in a single health state. We tested device independence. The same volunteers wore for popular in-ear models. The same stimuli and protocol are used for each headset. We ran our tympanic reflex detection on every model. The results were consistent across devices, with no retuning. Ear CSI is hardware agnostic. Users can keep the earbuds they already own. That concludes our presentation. Thank you all for your attention.